Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have discussed that what are the forces you will consider for the waterfront retaining wall, or if you have a water in your backfill or the seaward side. And now, today's class, first I will discuss about the pseudo dynamic approach, because in the previous lectures, those are pseudo static approach. So, as I mentioned, there are certain limitations. So, one is the time dependent behavior of the retaining wall, because your dynamic load is a time dependent loading. So, in this approach, the time dependent behavior is being incorporated again in a simplified form. Okay. So, first we will afford the pseudo dynamic approach. So, this approach was proposed by the Steadman and Zhang method. This is called Steadman and Zhang method. Okay, so it is simple pseudo dynamic method. It is a simple pseudo dynamic analysis, where the simple thing account, it can incorporate the phase difference and amplification effect within the backfill. Okay. So, behind the retaining wall. So, that means it can incorporate the phase difference, it can incorporate the amplification effect within the backfill. So, let us start this thing. So, before we start that, we are considering one retaining wall. Okay. So, this is a retaining wall, say, and this is your horizontal backfill and a planar failure surface. Okay. That is a planar failure surface. So, here what are the forces I will consider? The forces that will calculate. So, first what we will do, we take a very small segment we can consider, and then we will get that, say, this small segment whose on the failure surface, whose thickness is, say, dz. Okay. And this is the depth. Depth is, say, at a depth of z. Total height of the wall is, say, h. So, what will be this small segment length? The segment length will be simple, your capital H segment thickness is del h. The segment length will be, this one is capital H minus z divided by tan alpha. Which one is the alpha? Alpha is this angle. If this is the alpha angle, this one is also alpha angle, this is also alpha. If this is also alpha, then I can write that my tan alpha will be equal to that H minus Z, because this is Z, this one H. So, this one is H minus Z, H minus Z divided by the segment length. So, segment length will be H minus Z divided by tan alpha. This is the segment length and thickness will be dz. Okay, so I can write if the base is subjected a harmonic horizontal acceleration of amplitude AH, the acceleration at any depth Z below the wall can be calculated or written as A Z T. So, this is AH, this will be sine omega t, or we are providing that phase difference also. So, this will be omega t minus Z minus H minus Z into Vs. So, this H minus Z divided by Vs is that phase difference, or time required to travel the wave from base to that height or that depth of interest. So, where AH is the I can write this is the base is subjected to harmonic horizontal acceleration of amplitude AH, and AZ is the acceleration at a depth of Z from the top. So, this is the depth at a depth of Z. So, this is the acceleration, and the AH, the acceleration with the amplitude AH is applied at the base. So, that the wave will travel. So, it will take a time H minus capital H minus Z into the velocity of the wave. So, that will be the travel time, and that is your phase difference. So, that it is a harmonic motion. So, that is why we are written AH sine omega t minus that travel time required to the wave to travel from the base to that height or that depth. Okay. So, that travel path is capital S minus Z and velocity is the Vs. So, you will get your velocity, your travel path divided by the time. So, time will be travel path divided by the velocity, where Vs is the shear wave velocity. Okay. So, now if what will be the mass of that small segment? The mass of that small segment, that will be, what will be the area? Area will be length minus tan alpha into the thickness into the unit weight, unit weight gamma is the unit weight of the backfill soil, and divided by the G, because we are calculating mass. If I multiply the unit, it will give the weight divided by G. So, the mass will be simple gamma by G into H minus Z divided by tan alpha in dz, where gamma is the unit weight of the soil. So, the total force that will be equal to kHT. So, now I will calculate the total force. The total force will act like this. So, this will be the W, total W I am talking about. So, and your total force will be QHT, because now it is function of T as well as the depth. But here it is, initially it was a function of Z and the T, but now we are taking up the total force. So, it will be only function of T. But here remember that the vertical component is been neglected. Clear? But later on this vertical component is also been incorporated. But this is the first approach that I am discussing. Later on so many works are being done on this area. So, if you want you can get those papers and you will get the idea. But this is the first one. Okay, and we will discuss this first one. So, now here what is the total force? Total force will be integration 0 to capital H into, the force will be mass into acceleration. The mass at this segment is mz and acceleration at that point is this one, a z t into dz. Okay. So, mass is dz is already there. So, now if I put this value here, mass and the acceleration, and that will give you the force, horizontal force for the small segment. If I integrate this, it will give you the total force. So, it will give me the total force, okay, inertial force acting on the wall. So, that QHT is the total inertial force acting on the wall. So, after integration and putting the limit, I will get the final value is the lambda gamma h divided by pi 4 pi square g tan alpha, okay, 2 pi h cos omega zeta plus lambda sin omega zeta minus sin omega t, okay, where lambda is the 2 pi Vs by omega, okay. So, this is the wavelength of the vertically propagated shear wave, is the wavelength of the propagating shear wave, okay, and your zeta is equal to small t minus capital T by Vs, a capital H by Vs. So, this if I put the do the integration and then if I put the limit, I will get the QH expression. Clear? So, now I have that W I can calculate, QH I can calculate from here. So, now the force, if I put these forces QH, W and PA, similar to my this that Coulomb's method I have discussed. So, there the Mononobe Okabe has been extended. So, now we have three forces QH, T, W and the PA, and on that force if I draw with their angles, because we know their point of application direction we know, okay, point of application we do not know, but we know the direction. Now, if I put there makes that force triangle, then I will get from this triangle that PAE T, okay. So, the similar to the Mononobe-Okabe, okay. The total dynamic and the static force, that is PAE, that will be equal to QHT into cos alpha minus phi plus W sin alpha minus phi divided by cos delta plus phi minus alpha. So, alpha is given here, this is the alpha. So, you know what are the other forces will act. So, there will be a reaction F that will act as an angle of phi, that we know, and there will be, this is the perpendicular. So, PA will act PAET, now function of t, this will act at an angle of delta, okay. So, this height, say this is the, this height is small h, this is small h is the point of application. So, this is PAT. So, this is point of application is the small h, or so now these are the forces the similar way we did for the Coulomb's theory and then the Mononobe-Okabe theory. We will get finally the PAE is equal to QH cos alpha minus phi and plus W sin alpha minus phi divided by cos delta plus phi minus alpha. Delta, you know, the friction angle between the soil and the wall. And this is the total force that obtained by resolving the forces on the wedge. So, this is the total force. So, what is the forces on the wedge? So, these are the forces on the wedge. So, by resolving the forces on the wedge, okay, so we will get the PAE. This is your static plus seismic. But here the thing is that there is a time dependent thing is present, because QT is a function of t, you can see, okay. So, now but here your amplification effect is not been incorporated, but that also can be incorporated, but the phase difference is there. Now, the total earth pressure distribution on the earth pressure distribution I can get. So, this small PAE T is the total earth pressure distribution. So, how I will get that? Capital PA is the total force, active force, okay, static plus seismic, but PA is the earth pressure distribution. So, that I can get if I differentiate the capital P AE by del Z, because now this earth pressure is a function of T as well as the Z. So, by Z, then finally I will get, after doing the differentiation, I will get the value gamma in Z by tan alpha into sin alpha minus phi cos delta plus phi minus alpha plus kh gamma into z, kh, what is kh I have already discussed, divided by tan alpha then cos alpha minus phi divided by cos delta plus phi minus alpha into sin omega t minus z by Vs. So, this is the equation, two equation. By first equation you will get the total force, and the second equation, this if you differentiate it with respect to z, we will get the earth pressure distribution. Now, similar to that HD, the point of application, we will get the point of application HD. If you say this is the HD, so point of application will be H minus the point of application will get 2 pi square H square cos omega zeta plus 2 pi lambda h sin omega zeta minus lambda square cos omega zeta minus cos omega t divided by 2 pi h cos omega zeta plus pi lambda into sin omega zeta minus sin omega t. So, this is the expression of this HD. Now, you can see the point of application of dynamic thrust for very low frequency motion. So, very low frequency motion means you can see that your lambda is, if this is very low frequency motion, which indicates is very low h by lambda, because this low frequency motion h by lambda, that very small value, you will get HD will be exactly h by 3. But for very high frequency motions, the point of application moves higher on the oval. So, if I see this, show you this chart which is developed by Steedman and Zhang, considering kh equal to 0.3, 0.2. If you see, if your h by lambda value is very small, then it is exactly h by 3, this point of application. Okay, HD or h small d, you can see this is small d. So, h small d, because this is your small d value. So, this small d is exactly h by 3, but as this h by lambda value increases, then this point of application also shifts towards the upper side of the wall. Okay? So, that means it also shifts to or moves higher on the wall or to the upper side of the wall. So, that means for small h by d, h by lambda, small h by lambda, you can see that HD is your h by 3. But as this h by lambda increases, this value increases, h by lambda, lambda is the wavelength that I mentioned. So, h by lambda value increases, that this point of application also moves to the higher side of the wall. Clear? So, this is your pseudo dynamic approach. Here you can see in the simplified form the time effect is been incorporated. So, in the pseudostatic it is more simple, no time effect, but here this is also a simple approach. So, where more time effect is been incorporated. But if you want to do the real dynamic analysis, then you have to use by numerical tool, by using your advanced constitutive model that can be suitable for dynamic loading. So, those you have to use, and you can do that real dynamic analysis. So these both the approach, both are simplified, but one is without time effect, another is the time effect been incorporated. Similarly, your seismic amplification factors and the phase difference are also can be incorporated. Okay, so now I will, as I mentioned, I will solve one particular problem on this waterfront retaining structure. Okay, so I will solve one example problem and I will show you that how we can consider the forces. So suppose for this is our the structure or retaining wall. So suppose here this portion is below foundation. So this is your foundation, you can say. This top width is 1.5 meter and his bottom is 3.5 meter. And this one is say 1 meter. So that means this is 1 meter, this is 1.5 meter, this is 1 meter. Okay. And this is your backfill, which is horizontal backfill. Water table is 1 meter below the backfill in both the side. Both the side it is 1 meter below the backfill. This is my water table. Clear? So this one is 1 meter. Total height of the wall is 6 meter. Okay, and this unit weight of the water is 10 kilonewton per meter cube. Okay, so that I will write separately, because this place I will use to show the forces. So I can write I will give you the properties. The unit weight of the concrete. So this is a concrete retaining wall, which is 24 kilonewton per meter cube. Obviously, the I value is equal to 0. Now, what is the beta value? Beta value we can easily calculate, because you know this is 1 meter, this is 6 meter. What is this angle? This angle is coming out to be, this is 1 meter, this one is 6 meter. So, this angle is coming out to be 80.54. So, this angle is 80.54 degree. Okay. This it told that the angle is xi or psi. Xi angle is, you can say psi also. Psi angle is 80.54 degree, psi angle. So this is your psi is 80.54 degree, and beta you know that is 90 degree minus I. 90 degree minus I. So it will be 90 degree minus 80.54 degree. It will be 9.6 degree. So beta value is 9.6 degree. So this is the beta, which is 9.6 degree. Okay. Now your psi is 80.54 degree. Now other values I am giving, your C value is equal to 0. There is no question in the backfill. Now phi value in the fill is 35 degree. Your gamma sat, saturated unit weight is 20 kilonewton per meter cube. Gamma bulk or gamma dry, that means the unit weight above the water table, is 18 kilonewton per meter cube. Okay. Gamma water is 10 kilonewton per meter cube. Now delta value, okay. So that delta value is given, delta in the field, delta is given 28 degree. Okay, RU value, which is del U by sigma V dash, that is taken as 0.5. So now your lambda value will be how much? Lambda value will be 5 by capital H, which is 6. So directly I can write lambda is small h by capital H. So it will be 6. So it will be lambda is 0.833. So it is not a fully saturated case, it is partially saturated case. Clear? Now your Kv value is given, Kv is 0. That means the vertical coefficient is not, vertical component of the seismic force is not taken, and Kh is equal to 0.1. So later on I will check whether that 0.1 we can apply or not. And Q allowable, that means the allowable bearing capacity of the soil is 250 kilonewton meter square. So that part I am not calculating, that how to, that is under seismic condition also you can calculate the bearing capacity. That is not part of this course, so that's why I am not discussing that thing. I am discussing that that is been determined, and that value finally is given is 250 kilonewton per meter square. So we have to check the stress that is coming on the soil should be less than 250 kilonewton per meter square. Okay. So Q allowable, that means allowable bearing capacity of the soil is 250, and obviously soil means here base soil. So it is, I should write that this is the base soil. Okay. So in addition to that, some other properties are given. What is those properties? So base soil properties. Base soil properties mean these soil properties. This is the fill, backfill. This is the base soil. This is base soil. What is this base soil properties? It is given the phi base phi, friction angle of the base soil is 37 degree, and delta of the base, delta B, or sometimes it is written as phi B in few my derivation. So that is also the delta means the, and phi B means the friction angle between the soil and that wall or that material, which is taken as, given as 0.9 of phi base. So that value will be 0.9 of 37 degrees, so 33.3 degree. And C value is 0, and gamma obviously set for base, that is 20 kilonewton per meter cube. So these are the base soil value. Q allowable is also for the base soil, and then these phi F, delta F, these are the field soil value, gamma sat, gamma bal, gamma W, these are the field soil value. So that means this is the difference between, this is the field soil part and this side is the base soil part. So these are the all properties are given. Now I have to check the stability of this embankment or this wall. If it is stable, fine. If it is not, then I will make the embankment or make the retaining wall stable. So I will show this how we will check the stability for this retaining wall in the next class. Thank you.